Hello, ladies and gentlemen. I'm back. We're going to talk about Chapter 1 of ECE 103. Okay, engineering history. So, we've gone through several phases in civilization. We had very much a trial and error period. Roman Empire, Egyptian Empire, Marine. This was the beginning of the scientific revolution. Materials, steel, and so forth. Formal schools of engineering first started about the time of the American Revolution. Mechanical engineering, we got the scientific principles of mechanics going. Uh, Colleges were established. We started developing these different disciplines within engineering, and there was a transition to science-based engineering from trial and error, Leonardo da Vinci type sketches, I'll get into that in a minute, to modeling. We try to understand what a product is going to do before we actually build the product. And products are getting a lot more complicated too. So, we went through the rules of brainstorming. Think about how engineering impacts your lives today. And there's a ton. Obviously, we're not in class, so we can't do it as a group. But plastics, home construction, engineered wood, the technology to actually make a 2x4 these days. They precisely measure it, things like that, and deliver it. The trucks, automobiles, trains, all of them involve engineering, plus airplanes and cell phones, and you name it. The roads, it takes a civil engineer to build a road, to build a bridge, structural engineers to build buildings, and so forth. So there's engineering these days impacts our lives enormously. Enormously. Engineering design overview. So let's go back to the way people used to do it. So here's a drawing by Leonardo da Vinci. And very detailed. Great sketch. This was a wheeled catapult, a big catapult type machine that could launch objects. It could have changed, before the cannons, it could have changed warfare. And it was mobile. So with gunpowder, then people figured out mobile artillery. He showed worm gear, for example, on how to actually pull the thing back to load up projectiles. And here's a screw. Here's another type of worm gear type arrangement. Or actually, this is a screw. This is a screw type arrangement to be able to cock this mechanism with one person. Notice there's just one person down here. Okay. No dimensions. You do get a sense of scale from this little drawing of the person, but otherwise no dimensions. In our modern era, we need to be much more precise. Okay. So we've developed a design process, and the one we will use for this class, you see it here. 3 main phases: problem formulation, problem solving, and solution implementation. And here's some acronyms: no dogs sniff red ants, gas, pie. For identify needs, define problems, search, and then requirements, identify requirements. And then generate alternate gas, generate alternatives, analyze alternatives, select top designs. Plan, implement, evaluate. These are your design drawings at the planning stage. You've selected a design. You can start this partway through. finalize the design drawings, prepare that Gantt chart, finalize your Gantt chart. So you'll start a Gantt chart at the beginning. How long will it take you to do this? And I'm expecting you to have it done, I believe, by the 4th week. And same thing, this is due like the 8th week, and this is due like the 12th week, and then it gives you time to go back and iterate this process, which happens. You can't do this in one shot. Most of the time a project takes more than one. Most of the time a project benefits by prototyping. Try your ideas out on a smaller scale. The 3 main phases right here, 10 steps. And it might not be linear. This shows a linear progression, but you might have to skip back and forth, and that's common. This is a process. The steps you arrive at the design, methods you use, methods to decide how to do things, product, specifications that describe an artifact, and components with directions to assemble. Okay, so we go through the design, and now this shows the kind of iteration. Let's go to the previous slide. This shows the iteration you might have to do. Here's another picture. Different people have different ideas of what the design process should look like. So this fellow named Pugh came up with his design process. And he did market analysis, economic analysis, specification. To us, that would be the design requirements. They're very similar. So concept design, that would be problem solving, what we call problem solving. You'll notice the arrows go up and down, and meaning that you might have to go back and forth. Decision making, so now you come up with your detailed design. Optimize, then you manufacture. So this roughly corresponds to the steps that we are using. All design processes look pretty close. Here's another one by Paul and Beetz. Define the task, plan and clarify the task, analyze the market, select ideas, and so forth. And then you have a requirements list. This is the end of our first phase. Planning and clarifying the need, or the task. They call it the task. And then settle on a solution. Figure out, do all your research and analysis, and settle on a concept that you're going to use. Conceptual design. How are you going to approach this problem? And then preliminary layout. That would be your planning stage in our design process. And then make the stuff, and you have document it. Detailed design. Prototyping. This might be called the prototyping stage, and so forth. So you can see that anybody's idea of a design process is very similar. And the one we use, the one your book author uses, is as good as any. Okay. Here's another way to look at the design process as being a spiral. You might have to go through this spiral several times. Definition from ABET, American Board of Engineering and Technology, Accreditation Board. Design is a process of devising a system, component, or process to meet the needs. It's decision making, often iterative. Basic science, math, and engineering sciences are applied to convert resources optimally to meet these needs. It's a process, not an event. It's not a recipe. It's systematic, not trial and error. Trial and error is what the ancient Romans and Egyptians did. A lot of you guys are used to going into your shop and crafting something. We are not talking about crafting. We're talking about design. You plan what you're going to do and then you do it. You don't do something and then document it later. That's the difference. Craftsmanship. You craft something and then write down what you did. Design. You plan what you're going to do and then you go and make it. And you get agreement from everybody. Design often takes a lot of people these days, so you need to get everybody to get on board to sign up for it. Process manipulates resources from a supplier and produces outputs for the consumers. The engineering design process. This shows a linear process, but as I pointed out earlier, it's not necessarily linear. And this illustrates the three phases: formulation, solving, and then implementation. You might have to go back to previous steps. So, why might you need to go back? Here's some answers. Here's some ideas. You might find out that additional needs come up and you have to develop other alternatives. You might get to the very end and figure out, oops, that it didn't perform as expected. And this is actually what happened on the Apollo moonshots. So NASA was planning on building a giant rocket that would take everything to the moon and back. And they either planned an Earth rendezvous, so you'd be launched into space and you'd orbit, you'd rendezvous with your lunar transit vehicle, and it would have all the life support and everything for the astronauts to go to the moon, land on the moon, come back, and come back to Earth. And then they also had direct flight, where you'd launch from Earth, you'd have a big massive spaceship that would go to the moon, land on the moon, everything would go. And what was decided upon eventually, but it took a lot of effort, the engineer had to really sell his idea to NASA, was what's called a lunar rendezvous. All the stuff you need for life support for going back and forth to the moon would be carried in the capsule. And then you'd have a lunar landing module, which would be minimalist. It'd be much smaller, and descend to the moon and come back from the moon. And then the capsule would go on back to Earth. And by the way, they slammed these lunar modules into the moon to measure earthquakes on the moon. That was a way they could get a sounding and figure out the internal composition of the moon. So it saved them. There was plans to build a Jupiter rocket bigger than the Saturn V. But because of the lunar rendezvous, they were able to go to the moon with a smaller, less powerful Saturn V rocket, although it itself was huge. So this was where they got way down the process. The lunar shot was, they got way down the process and then figured out that there was a better way to do things. So new requirements might become apparent when you get to build it. So you have to go back to there. That's almost back to the drawing board. You might identify some requirements that weren't apparent when you tried to figure the problem out, and so forth. The amount of time it takes can depend if you're adapting a previous design or doing something from scratch. By the way, I want your teams to do something. You've got to generate your own design. You can use things others have done, but when it gets down to it, you have to do something. Part of your design has to be yours. Your design, not somebody else's. By the way, the last point, a lot of things are done concurrently. Okay, engineering design. Here's different ideas of the design process. Not trial and error, systematic, identifies needs, explores alternatives, tests and evaluates alternatives, does not rely on luck. So, you should know what that basic idea what the design process is. We'll get into details later. How do you apply it to meet a set of needs? And know the three phases and how it's adaptive and systematic. Code of cooperation, I mentioned that earlier, that here's an idea to encourage everybody's participation. Let's go back a step, let you guys see that. That's in 8. So you've got an idea of what to do on the engineering notebook and a code of cooperation. You can create your own, by the way, and especially online. You will log in and so forth. You will use Google Hangouts and so forth. Okay, that's it for chapter 1 of the book. This covers the PowerPoint slides for chapter 1.